Thank you. You know, by far the largest and most interesting part of my job as BP's chief scientist is to help plot and now implement the company's long-term technology strategy. The way I like to think about it is to figure out what beyond petroleum really means. Being new to the energy business when I came into the company just 3 years ago, I set about trying to understand the background in which the strategy would be plotted, and over the first year and a half or so managed to achieve what I think is a fairly synthetic and synoptic understanding of the energy system, where it's likely to be headed, and what technologies are likely to be important over the next 30 years or so. And as I started talking to people about what I was learning, a common reaction was, "Oh, really?" And so what I'd like to do today is to take you through some of that thinking, understanding what energy trends are and what technologies are likely to play a role in addressing some of the very substantial issues that society faces in terms of its energy production and use. So when you start thinking about energy technologies, the first thing you realize is that it's not about the technologies alone. Indeed, the technology choices and the policies that drive them are conditioned by the social, economic, and political contexts in which the technologies are employed. And we came to understand that there are really four forces driving energy and energy technologies. One of them is the strong growth in demand. A second is the challenges in supplying energy to meet that demand. A third is the issue of security of supply. And the fourth are the environmental impacts. And all of these drivers need to be understood before you can talk about technologies and the policies needed to drive them. So I want to take you through each one of these drivers, and then we'll turn to the technologies themselves. Under the growth in demand, the headlines are, first of all, very strong growth in demand projected for the next several decades, due in part to GDP growth and also to the growth in the world's population. There is also the issue of the rapid urbanization of the world's population. Right now, just about 50% of the world's population lives in big cities, and that number is expected to grow to 75% over the next 25 years. And then, as always in demand, there is the issue of demand management and what it can bring to the problem, and I'll say a few words about that. So let me start with this chart, which for me is iconic and summarizes so much about what has happened and is likely to happen with the world's energy. What we plot here is the primary consumption per year per capita in gigajoules against the GDP per capita in constant dollars. And what are shown are evolutionary trajectories for about 24 or 25 years for various countries. And when you look at this chart, a number of things jump out at you immediately. The first is how out of whack the U.S. is with everybody else. The second is that while the U.S. is high, it's high in both energy consumption and in GDP per capita, its energy use is growing relatively slowly compared to other trajectories. We then have a number of other countries in the OECD, the developed world, that have an energy use per capita of about half the U.S.'s, and also growing relatively slowly. There are some fast movers on the chart. Ireland, for example, look at that. There are some countries that exhibit what might be called a retrograde motion. Russia, due to the economic turmoil in the 1990s. Russia only goes from 1992. And then there is a broad swath of countries that follow a more or less universal trajectory of increasing energy use as income increases. And what is sobering about this is that you realize that there are about 1 billion people between the U.S. And the other OECD countries. There are another 2.5 billion people in China, India, Brazil, and then there are another 2 billion people not on the chart at all. And what we expect to see is that as these countries develop, we expect to see strong energy growth as they climb up this main sequence, if you like. There was some indication, by the way, China a few years ago claimed that it was off the trajectory, and in fact it was, but you can see that very recently it's come back on, perhaps due to better statistics. The other strong driver is population. This is the world's population since 1750, and it's projected to top out at about 9 billion people by the middle of the century and be roughly constant after that. What's interesting is that most of the growth happens in Asia and Africa, and in fact Europe and North America are relatively static in population over the next 50 years. That strong growth in GDP and also growth in population drives a very strong growth in demand. Over the next 25 years, we expect to see something like a 50% increase in energy demand, most of that driven by the growth in the developing countries, some of it driven by growth in OECD. This makes the point a little bit more dramatically. This is 30-some-odd years of energy demand for different regions. So North America has been going up like this, Latin America, Europe. This is absolute now, not per capita, and Asia is really the one to watch here. An interesting number, by the way, just to get a sense of growth, particularly in transport, is that in the next 20 years, more cars will be built than have been built in the entire 20th century. So this is the development of a great swath of the world's population in the next several decades. It's interesting to look at the growth in energy demand by sector, and this is both historical and projected. Most people, when you say energy, think immediately automobiles and petrol, and that's perhaps natural living here in Southern California. In fact, only about 25% of the world's energy goes into transport. About 40% of the world's energy goes into making electrical power, and another 40% goes into making heat in various forms, whether it's for industrial processes or for building heating. And as the world develops, we expect to see disproportionate growth in the transport sector, since mobility is something that people like to purchase as they become richer, and disproportionate growth also in electrical generation, because the clean energy of electricity is again favored in developed countries. Okay. A couple words about energy efficiency and conservation. This is always discussed and often invoked as a way of managing this demand. Demand depends more on various factors than it does on GDP. It depends on the geography, big country, small country, climate, heating, cooling, demographics, the way cities are built, the economic mix, factories versus offices, technology choices, and so on. One illustration of the great diversity of efficiencies is that in Japan, they only use 1/3 of the energy per transport that is used in the US per capita. Right. Efficiency through technology is about paying today in the anticipation of savings tomorrow. So you might put in a more efficient furnace in the expectation of saving on gas bills in subsequent years. It has to be cost effective to be attractive, otherwise it's not going to happen. And it may not reduce demand, either through misuse or in supply-limited situations. So, for example, if there is now not enough electricity in China to power all the air conditioners that China may need, making air conditioners more efficient will not reduce electricity demand, but it might make more Chinese comfortable. Similarly, efficiencies can be misused dramatically. Here's an example from the US automobile fleet in the 1990s. The new cars sold in that decade actually went up in miles per gallon by about 4.5%. Not great, but when you open it up, it's a little bit more surprising. Engine efficiency went up by 23% in that decade, a rather amazing number in terms of power per weight, but it was eaten up by people driving bigger cars, SUVs, and by having the performance go up. And in fact, that ate up 18% of the gain. And actually, when you look in that decade, the annual miles driven went up by 16% per vehicle, and the annual fuel consumption went up by 11%. So in fact, efficiency alone is not enough. It is really about conservation or consumption that one needs to worry about when thinking about managing demand. Okay, let me turn to the second issue, which is about energy supply. And the headlines here are, first of all, there are significant resources in the world for the next many decades, but we're going to see a rise in non-conventional resources for various reasons. This is a great chart. I like this. It shows where the U.S. got its energy over the last 150 years. And what is shown is the percent of energy obtained from various sources. And you can see in the Civil War era, the country got almost all its energy from biomass, from wood. And that as the Industrial Revolution set in, we see coal taking over, a little bit of hydropower. As the mobility revolution happened in the early to mid 20th century, oil became very important. Gas has recently been displacing oil to some extent, and then nuclear is a little wedge over here, and renewables, about which we'll have more to say in a moment, is that tiny pink band up there. What's interesting is that the absolute amount of energy in 1850 from wood is the same as the absolute amount of energy in the year 2000. It's just that the energy demands of society have grown so much, and one has found other more convenient sources. Okay. So the lesson here is that people can and do switch their energy supplies as circumstances, whether technology or economic, warrant. This shows for the world where it currently is getting and historically where it's gotten its primary energy. And what you can see is that currently 36% of the world's energy comes from oil. That has been falling over the last 35 years. Coal accounts for about 28%. That was coming down but has experienced a resurgence in the last few years, and we'll talk about that in a moment. Gas has been climbing and is now 23.5%, and hydro and nuclear account for 6% each and have been roughly flat over the last 20 years. There are various uses for energy, and the way the world has constructed its energy system, different primary sources feed different uses. So the world, let's see, in 2004 or so, used about 186 million barrels of oil equivalent per day. Don't worry if you don't know how to convert barrels of oil equivalent into gigajoules or whatever your favorite number is. It's only the relative things that matter here. Transport used 37 of that 186, so that's about 20%, as I promised. Buildings used 56, industry used 45, and power generation used 76. So just about, well, whatever that is, 40% or so of that. We start with oil, and you can see that oil is mostly about transport. By far the largest fraction of oil goes into transport. The balance goes into industry a little bit. People still heat their homes by oil in some cases, and oil and power generation is only a relatively small number. Gas, you can see, is roughly evenly split between home heating, industry, and power generation. Coal, which supplies 43 of the 186, is almost all about power generation. Biomass, the world still gets a significant fraction of its energy from conventional biomass, is mostly about fires in buildings, heating and cooking. Renewables, 5 of the 186, all in power generation. And then finally, nuclear, 14 of the 186 in power generation as well. So if you look at the whole picture, it's a little bit complicated, but the lessons to draw are, first of all, coal is mostly about power. Oil is about transportation, and transportation is about oil. And then these various others contribute to both power and heating. Important distinctions to keep in mind. Let's look at business as usual, BAU, of where the world is going to get its energy over the next 25 years. And you can see that currently the world gets just about 80% of its energy from fossil fuels: coal, oil, and gas. Projections at these reasonable or plausible growth rates show that by 2030, the world will still be getting the vast majority of its energy from fossil fuels. Renewables, other renewables, non-hydro renewables, or non-biomass, are growing the fastest, 6.5%, but from a very small base and will not be significant, again, business as usual, over the next 25 years. And you can have enough fossil fuel resources in order to satisfy that demand. The answer, I believe, overwhelmingly is yes. This shows for the three fossil fuels, oil, gas, and coal, on an absolute energy basis, how much there is, how much oil is known to be in the ground, so-called proven reserves, how much the geologists believe is plausibly there yet to find, and then unconventional oils, heavy oils, tar sands, shale oils, and so on. And you can see that at the current rate of consumption, the world has 40 years of proven reserves. Now, of course, reserves migrate from the yet to find to proven as people go out and look for them, start to produce them, characterize them, and so on. For gas, the world has known 67 years, another equal amount plausibly there, and lots of unconventional gas, for example, in the hydrates at the bottom of the oceans in the Arctic. And then finally, coal is the big gorilla here. There are 164 years of coal known to exist at current consumption rates, and no one has gone seriously exploring for coal. It's believed that perhaps up to 1,000 years of coal exist in reasonably accessible forms. Oil is the one that everyone worries about the most, in part because of the international trade involved and because our transportation is so dependent upon it. This is a chart from the International Energy Agency, and it shows how much oil is available in billions of barrels at what economic cost is it to produce. And you can see that the world has already produced in the last 150 years about 1 trillion barrels of oil at a very low cost. The countries in OPEC in the Middle East have about another 1 trillion barrels known to exist or thought to exist. Other conventional oil outside of the Middle East is also about 1 trillion barrels. And then other sources, deep water, the Arctic, enhanced oil recovery, about which we'll say more in a moment, heavy oil and bitumen and oil shales comprise about another 4.5 billion barrels, trillion barrels of oil, all at prices that are less than today's roughly $60 a barrel. Of course, it was as high as 70-something during the summer. The world will need, in the next 25 years or so, about 1 trillion barrels of oil, the width of that red bar. All right? That, by the way, that corresponds to about 100 million barrels a day average consumption. Right now, at about 85 million barrels a day of consumption. That will grow over the next 25 years. We'll average about 100. So I look at this chart and conclude that the world is not running out of oil anytime soon. We may pay more for it if it becomes more difficult to extract, and these more difficult places cost more, but we're certainly not running out of oil. Okay, however, there are problems with some of the fossil fuels, and that's got to do with security of supply. In particular, the dislocation of resources relative to where the demand is and the growing dependence on imports in most of the consuming countries. This chart shows where the fossil fuel resources are around the world in billions of barrel of oil equivalent, all on the same energy scale. And shown is conventional oil, unconventional oil, gas, and coal. So let's start with the Middle East, where we know all the oil is, and to a first approximation, that's true. That's a big bar. A little bit of unconventional, a lot of gas in the Middle East also, no coal. If we look at North America, what we see is not very much conventional oil, a lot of unconventional oil, and that's the tar sands and shale oils that you have probably heard discussed, a fair bit of gas, but a lot of coal. If we look at Asia Pacific, China, India, Japan, not much oil, some gas, and again, a lot of coal. And if we look at the former Soviet Union, they lucked out. There's a good bit of oil, a lot of gas, and a lot of coal. Europe, as you'll see, not much. So the lesson here is that the coal is where the people are, and the oil is where the people aren't. And that leads to good trade in some of these commodities. Just to make that point a little bit more dramatically, if you look at oil and take the three largest energy markets, North America, Europe, and Asia Pacific, those three markets consume 78% of the oil produced every day, but they have only 10% of the reserves of that oil. Great mismatch. For gas, similarly, they consume 61% but have only 15% of the reserves. And for coal, it's much more evenly matched. And so other things being equal, you might expect that the consuming countries are going to be turning increasingly to coal if they're worried about security of supply. And in fact, that's starting to happen in China. This just shows more graphically the growing international trade in energy. We have the exporting regions, Africa, Middle East, former Soviet Union, and South and Central America are all exporters and are growing in exports with time. The consuming countries, Europe, North America, and Asia Pacific, are all increasingly importing with time. As you probably know, the U.S. right now imports about 60% of its oil from outside the country. Okay. Let me then turn to the issue of environmental impacts, and there are really two here. One is local pollution, as comes out of smokestacks and automobile tailpipes. To my mind, this is largely a technically solved problem. Here in the U.S., we've seen an increasingly stringent series of regulations driving technology to the point, for example, when I lived for 30 years in Southern California, you could feel and see the air get palpably better, even though more people and more vehicles and more economic activity took place in the LA basin. So it is a matter of the willingness and ability to apply technology at cost. Here in the West, we have decided to do that with the obvious benefits. If you go around China or India, you realize that they haven't gotten to that point yet, but very likely they will soon because the deleterious effects of the local air pollution are just awful. The issue of climate change, though, is a much more difficult one to understand, to talk about, and so I want to spend a little bit of time on that and its relation to energy and energy technologies. So climate change and CO2 emissions. My take on this, the basic facts, CO2 is going up, and it's going up largely due to fossil fuel use. Keeling curve, familiar to all of you here at UCSD, I hope, from pre-industrial values of 280 parts per million CO2 to about 384, I think, currently in this last year. The global temperature is clearly going up as well. This is the official NOAA record over the last 120 some odd years. Strong increases, particularly since 1980 or so, going up. There are other indicators of climate change which you read about in the newspapers, and I'm not going to dwell on at all, but it's pretty clear the climate is changing. There's a plausible causal connection between them. You can do the back of the envelope numbers, and it's about right. The temperature's going up in concert with the increases in greenhouse gases. But it's a scientifically difficult problem. We're looking for about a 1% effect in an intrinsically noisy system, and there are lots of other forcings that complicate the problem and our ability to really pin down the anthropogenic causes and what's likely to happen as the CO2 keeps going up. The impacts of CO2 are quite uncertain, both on the climate system itself and then the economic impacts that follow from it. However, many people have discussed a benchmark stabilization value for CO2 in the atmosphere of 550 parts per million, twice the pre-industrial concentration. Under business as usual circumstances, if you just take the Keeling curve and extrapolate it, you hit that by 2050, mid-century or so. And many people believe that 550 is in fact even too high and that we will start to exert dangerous influences on the climate at 500 or even, in some extreme cases, at 450 ppm. Despite the scientific uncertainties that might remain, and they're becoming smaller as time goes on, precautionary action is clearly warranted. This is not a good thing to be doing to the climate system. But the real question that I want to address is what could the world do to forestall this, to stabilize greenhouse gases, and will the world do it? And these are very difficult questions. I want to take you through some of the technical and political and social background associated with those questions. There are two things you really have to understand if you're going to grapple with the CO2 problem. The first is that the Earth absorbs CO2 only at a limited rate. We're putting it up there at rates that are just too large for the system to absorb. In fact, emissions would have to drop to about half of their current value by the end of this century if we hope to stabilize at 550. So we're going to have to cut the rate at which we're putting CO2 into the atmosphere. This has to be done in the face of a doubling of energy demand over the next 50 years and a projected 1.5% per year growth in emissions. So by the end of this century, our energy system has to be at least 4 times more carbon efficient than it is currently. Right? Half the CO2 emissions with a doubling of energy demand. The second very disappointing aspect of this problem, which many people don't realize when you talk to them, is that CO2 lives in the atmosphere for a long time, certainly longer than any of the timescales of interest in this problem, about 1,000 years. Actually, it's long enough that it doesn't matter exactly what the exact value is. And that means that the atmosphere is going to accumulate emissions in this century. The good news is that it's the integral of the emissions that matter, and so we could emit a little more now if we're willing to cut back harder later. But the bad news about that is because our emissions are growing exponentially, if you make modest changes in those emissions, you only delay the time at which you cross a danger line. You don't prevent it. In other words, the bathtub just keeps filling up. It fills up a little bit more slowly. A good rule of thumb is that if we manage to reduce our emissions growth by 20%, that buys us 15 years of time. That's the 1.5% a year exponential. So not only do we have to reduce emissions a little, we got to reduce them an awful lot if we're going to have an impact on this problem. Here are some scenarios that my friends in Princeton, Rob Sokolow and Steve Picala, ran for us just to illustrate what's going on. This is emissions, and this is time. You can see historically, and then the projected 1.5% a year rise. The concentration correspondingly under business as usual rises up exponentially as well. It's essentially a linear system. If you drive it with an exponential, it'll respond exponentially. If we wanted to stabilize at, let us say, 550 ppm, we might be able to follow one of these green trajectories, either letting it go up and then cutting back hard, or essentially flat topping now and cutting back more gradually. If you want to stabilize at 500, it's one of these blue trajectories, or at 450, it's one of the red trajectories. Right? So this is the challenge in terms of emissions if we want to stabilize atmospheric concentrations. There are lots of reasons why society is going to find it very hard to do this. First of all, the climate threat is intangible and can be masked by natural variability. You may remember 2 years ago, there was some talk about the very severe hurricane season in the Gulf as being a signature of climate change. Of course, last year, the Gulf was unusually quiet in terms of hurricane activity. So there's a significant natural variability in the system that obscures climate change. I would contrast that with ozone or air pollution, where in fact the effects are very real and immediately evident to the populace. The second is, unlike CFCs, for example, in the ozone problem, energy is at the heart of economic activity. As I showed you, energy is highly correlated with GDP. So it's not as though there's some simple magic fix here of just switching some chemicals from the CFCs. The other part, which is more a social issue, is that the CO2 timescales are very poorly matched to the political process. As I showed you, the rise time for CO2 emissions is 67 years. CO2 lives in the atmosphere for centuries. On the other hand, the energy infrastructure takes decades to replace. Power plants are being planned now that will be emitting by mid-century, when the concentrations will hit 550 under business as usual. Buildings in which half the world's energy is used typically last about 100 years. Automobiles last 20 years or so, in which the petroleum energy is used. And so it's hard to make immediate changes in the system. Moreover, you compound that with the fact that the political cycle is about 6 years. The news cycle is about a day. And it's hard to keep people's attention focused on this problem and what to do about it. And there will be inevitable distractions. We're going to see, if the historical temperature record is any guide, a few years of cooling. We're going to see economic downturns, and believe me, this is going to cost money, at least in the short term, to fix. And there will be unforeseen expenses, most recently Iraq, tsunamis, et cetera, et cetera. So it's going to be difficult to keep society's attention focused on this for a sufficiently long time. And perhaps the greatest problem is that emissions, the economics associated with them, and the priority of the climate change threat varies greatly around the world. This picture, which is very similar to the one I showed you at the beginning of this talk, plots CO2 emissions per capita against GDP per capita, and it looks pretty much like the energy picture. The OECD countries are emitting a lot, but there aren't all that many people in them. The developing countries are emitting not very much, but they have a lot of people and are expected to see their growth go up strongly as they develop economically. There are two interesting anomalies on this chart if you compare it carefully with the energy chart. One of them is France. Why is that? France is low on this chart. It was up here with everybody else. The answer is that France gets 80% of its electricity from nuclear power, which doesn't emit any CO2. The second is Brazil. Brazil is low on this chart for two reasons. One is that there's a lot of hydropower in Brazil, and the second is that Brazil gets a good fraction of its road transport energy from ethanol, which again doesn't emit much CO2. So there are lessons there about how we might be able to reduce CO2. So what are the implications of these different levels of emissions around the globe? What it means is that in this century, emissions from the developing world are going to be more important than those from the industrialized world. The developing world emissions are growing at 2.8% a year versus the industrial world's growth at 1.2% a year, and they will cross over sometime in the next 15 years or so. So the picture looks like this. Emissions in time, developing world going up like that, industrialized world going up like that, and just about crossing. Those numbers have two sobering implications. When the emissions from both parts of the world, the developed world and industrial world, are about equal, namely about now, every 10% reduction that the industrial world can make in its emissions, and it has not yet managed to do that, that's compensated by less than 4 years of growth in the developing world. Remember that big curve of energy use in Asia that we saw back in the beginning. And the second is if you took India or China and made their per capita emissions equal to that of Japan, which is among the most emissions light of the developed countries, global emissions would be 40% higher than they are now, rather than being cut by the factor of 2 that we need if we're going to stabilize things. So when I was in academia and I looked at a situation like this, I would say there's a big problem here. In business, you're not allowed to say that. What you're allowed to say is that it's a challenge. So this is a challenge. Either way, technology development is going to play a central role in trying to deal with this problem. And so I now want to turn to the technologies and see what we can say about them. Oh, last graph before we get on. This shows, actually I have two more. This shows CO2 against energy, and there are lines here that correspond to coal, oil, and gas. You can see gas is the most CO2 light of the three fossil fuels. Again, different regions. The challenge here is to get outside of this fossil fuel envelope. And again, you can see that France and to some extent Brazil have managed to do that. The world currently is right there, right? And we need to stabilize our emissions while continuing to grow energy, so we need to move over this way. Finally, before I turn to the technologies, 2 reminders that it's not only about the CO2, there are other greenhouse gases. CO2 from energy emissions corresponds to only about 60% of the total greenhouse gas emissions. Other big users are land use. This is mostly deforestation, CO2 coming from deforestation. Agriculture, mostly nitrous oxides, and waste, methane, and so on, correspond to emissions that don't come from energy. Most people don't talk about that, but as you can see, they're about a little more than a third of the problem. How will they grow with time? And this is relatively interesting as well. You can see power will grow strongly over the next 45 years. The CO2 associated with the power will grow remarkably if business as usual holds. Transport accounts for only currently about 25% of total emissions, 20 to 25%, and that will grow more modestly, and you can see the others here, which I won't go through right now. Okay, so let me turn to technology and policy. Here is a big list of energy technologies. Technologies associated with primary energy sources, technologies associated with extracting energy from those sources and converting them, refining, for example, photovoltaics, et cetera, and technologies associated with how we use energies, urban infrastructure, remember, most people are living in cities, hydrogen storage, fuel cells, et cetera. When you look at this list, everybody immediately has their own favorites. And it's common to say, in the spirit of equality and ecumenity, if that's a word, ecumenical spirit, there are no silver bullets. And yeah, I'm willing to buy that, but I would also say that some bullets have a larger caliber than others. And the challenge for a company like BP, and indeed for the world, because we have only finite resources to devote to these problems, is to find where you're going to get the most bang for your buck in addressing the problems of energy. So how do we do that? How do we assess these technology options? There are issues about where is the technology currently and what is the technical headroom look like, all right? And so you might contrast the relatively mature technology associated with windmills, for example, with what you might imagine happening if you looked at biofuels more seriously. There's the issue of how much headroom is there technically. The second is the budgets. People often forget about that. How much does an option cost relative to others? How much energy does it take to go in versus the energy that comes out? What about emissions? Not only CO2, but also local air pollution. There is the issue of materiality. Many of the things people talk about just simply do not scale. The scale of the energy infrastructure and the scale of the energy problem is something many people do not appreciate. A threshold for BP is that a terawatt of power, which is roughly 5% of the mid-century business-as-usual energy demand, is something that we're willing to think about. Anything less than that is just too small to make a difference. There are other costs, reliability, intermittency, and so on. Sun doesn't shine all the time, wind doesn't blow all the time, and so you have to allow for costs associated with that. There are issues of social and political acceptability. Nuclear energy is perhaps the one that comes most obvious to mind, but as you may know, there are fights about where you put or don't put windmills in various parts of the world, off Nantucket, on the mountains in Scotland, et cetera, et cetera. And then also you have to be very clear as you think about technologies, what problem are you trying to solve? And as I've described it to you, there are really 2 problems that exist. Ideally, you would like to solve them both, but some technologies will address one problem more than they will another. The 2 problems can be conveniently characterized as follows. One is the concern over the future availability of oil and gas. You can read this roughly as oil price. Am I concerned? In which case the oil price might be very high. Am I not concerned? In which case the oil price is low. The other axis is how concerned are you about greenhouse gas emissions and the threat of climate change. and again low versus high, depending upon a society's concerns, individuals' concerns, you might adopt technologies that fall in one or the other of these spaces. So let us first look at the transport sector, and this is all about transport. What is important for transport is largely liquid hydrocarbons. You can't beat the energy density of gasoline or diesel in powering transport. It's 50 times better than the best battery we can imagine now, and about 10 times better than the best hydrogen storage system that the DOE can imagine. If you don't care very much about climate, but are concerned about the availability of oil and gas, you might look at processes that turn coal into liquids, coal to liquids. If you care about greenhouse gases, you might capture and store underground the excess CO2. Heavy oil, gas to liquids, and so on are all technologies that will play to energy security concerns, but do not play to CO2. Other technologies are shown here. Of course, this is only notional, but it gives you some idea of where things sit. Ideally, you would like to be in the upper right. And as you can see, the only supply side options that exist in the upper right are carbon-free hydrogen for transport, and I'll have more to say about that in a while, or advanced biofuels. Of course, vehicle efficiency is important in reducing use and hence emissions, but that's on the demand side. I'd like to concentrate for the moment on the supply side. A very important concept in thinking about transport fuels is the fungibility of carbon. We have the ability through chemistry and chemical engineering to take various sources of carbon, run them through some magical chemical steps, at least they're magical to me, I'm a physicist, and what do I know, and decorate those carbon atoms with various oxygens and hydrogens and produce diesel fuel, produce alcohols, produce power, if we like. And so the real question is, where are you going to get your carbon from in order to power transport? Because we can do all of this. Of course, there are inefficiencies and extra costs, but the question is, where are you going to get your carbon from? So in fact, let's look at where the U.S. got its carbon from and how it used it last year. If we look at the road fuels, transportation fuels, the U.S. used about 450 million tons of carbon in gasoline last year and about another 200 million tons of carbon in diesel fuel. And so altogether, 650 million tons. And you might ask, if I want to make a reasonable impact on this, I want to have a source of carbon that's going to account for, say, 15% of the 650, I need about 100 million tons of carbon somewhere in order to make up for that. Where could I get that? Well, you look at how much coal did the U.S. use in that year, and the answer is about a gigaton of carbon, 1,000 megatons. The U.S. has ample coal production capacity, and so it could get more carbon from the coal and use that to make transportation fuels. Easily doable. Or not so easy, but plausibly doable. Other fossil fuels, natural gas, other petroleum and natural gas liquids. This is petroleum that goes into petrochemicals. This is propane, et cetera. You can see you're on the scale of the transportation fuels, but we're already importing natural gas, and we need all the petrochemicals we can get. And so this is probably not a place to look for it. It is common these days to talk about biofuels in agriculture and to try to get some of our transportation fuels from agricultural products. And so it's interesting to look at agriculture on this scale. Here is corn. This is the entire U.S. corn crop, 120 million tons of carbon a year. You can see that even if you converted all of the corn into fuel, you would just make 15% of transportation. And that leaves nothing left to feed animals, to feed people, no corn syrup for sweeteners, to export, and so on. If you look at all the other agricultural products, I've gone too far. I want to go back up one. Yeah, good. There's corn. All of the other agricultural products are just too small to make a difference. I will draw your attention particularly to edible fats and oils. Biodiesel, as people talk about them, right? Willie Nelson and all of that. That's how much in total the country produced in oils. So you can't fry enough French fries to make a difference here, all right? What is interesting is if you look at how much unconventional biomass was used in the country, that was 100 million tons, mostly in paper and pulp for power, paper mills and pulp mills for power, and how much biomass the Department of Energy and Department of Agriculture plausibly believe that the country could produce if we made efficient use of our forests and grew some energy crops without impacting food production. All right? So the conclusion from this is if you want carbon to power your transport and you don't want it to come from petroleum, you're either going to dig it out of the ground as coal, in which case you have the added CO2 emissions, or you're going to grow it as biomass. That's all you got. This is the same picture for the world. I don't want to take the time to do it, other than that to say the same conclusions pretty much hold. So a word about biofuels today. They comprise 2% of the world's transport. They are used mostly with existing infrastructure and vehicles. There's growing support worldwide, and they run right now by converting food crops into ethanol or biodiesel. In the U.S., ethanol produced from corn is economic at $45 a barrel. And in Brazil, ethanol from sugarcane is economic at $22 a barrel. There are lots of questions about biofuels, but I see my time is running short, and I'm not going to discuss them in detail, but they are perhaps the obvious ones. I see I've got much too much material, so let me just flip through this and just talk about the technical challenges for a moment. What do we need to do if we want to do biofuels right to extract the maximum scale, energy benefits, and greenhouse gas emissions? What you really need to do is to take the petroleum value chain, which is how we explore for petroleum, get it out of the ground, move it around, refine it, and blend it, a chain that's been optimized over the last 150 years and is practiced very well by BP and other oil companies, and fuse it somehow with the agricultural value chain, which has been in existence for thousands of years. It is about producing food and distributing it, and creating a hybrid in which we don't use food crops but energy crops, process them efficiently, and produce fuel molecules. And when you think about all of the steps and the variables that exist, what crops are you going to grow? How much can you grow per acre? How do you cultivate these crops, because they're very different than food crops? How do you harvest them and transport them? How do you process them? In particular, how do you digest the very refractory cellulose and turn it into sugars that then can be fermented to fuel? And then what fuel molecules do you want to produce? Ethanol is by no means the best fuel molecule. Lots of science to do here, lots of engineering optimization, and it's something that, as Art mentioned, we in BP are making a big investment in. Since he's already mentioned the EBI, I don't want to say much more about it, other than that here at UC San Diego, it was an awfully credible proposal, but the competition was very stiff from a number of the other schools. Let me then turn to the power sector. Now, this is not about transport, but now we're going to talk about power. And again, in the same two-dimensional space, the big gorilla is coal. Pretty awful for climate change, but great if you're concerned about security of supply. If you look in the upper right, which is where you would like to be, we have nuclear as a pretty big option, wind to some extent, hydrogen power, which is another name for carbon capture and storage, whereby you use coal or natural gas, burn it in such a way that you can separate off the CO2 and pump the CO2 under the ground, where there's every expectation that it will stay for thousands of years, and then a circle up on top for solar. If we talk about electricity, it's sobering to look at where the world got its electricity in 2004. 40% from coal, 20% from gas, 15 or 16% each from nuclear and hydro, a little bit and a diminishing fraction from oil, and then 2.3% from other, which is mostly biomass, a little bit of wind, a little bit of geothermal, and 0.02% of solar, and even less of tidal and wave. The solar number actually used to be 0.01%. It's gone up in the last couple of years. All right? But again, if you want to make a difference, this shows where the big energy sources for electricity generation are. What about costs? These are costs of electrical generation. Cost of electricity, assuming some reasonable rate of return. This is 5 cents a kilowatt hour, just to set the scale for you. By far the cheapest is coal at $40 a ton. Gas is more expensive. This assumes $4 gas. It's currently about $7, but probably it will come down. Somewhat more expensive. Other options, which are low or zero carbon energy sources, are significantly more expensive. Carbon sequestration of gas, carbon sequestration of coal, nuclear, onshore wind is economically competitive at good sites. And not surprisingly, many people, including BP, are deploying a lot of wind these days. Offshore wind, significantly more expensive because you've got to work out in the water. Biomass gasification, wave and tidal, look how expensive it gets. And then solar retail cost. This is how much it costs without subsidies of any sort or incentives from the government to generate electricity. This curve is really central to understanding CO2 mitigation. I want to spend a minute on it. It shows the cost of electricity in cents per kilowatt hour, so this is 6 cents, as a function of the carbon cost, if you assign a cost per ton of emitting CO2, and various technologies. So conventional coal starts out the cheapest if you don't price CO2, but then climbs rapidly as the cost of CO2 goes up because it emits a lot of CO2. Nuclear, for example, is more expensive, as we saw on the previous chart, but doesn't change as the CO2 cost goes up because it doesn't emit CO2. Similarly for onshore wind and so on. And what you see is that at a cost of somewhere between $20 and $40 a ton of CO2, or up to $150 a ton of carbon, that the lines start to cross, and you will get carbon out of the power system if you assign that much of a cost to CO2 emissions. Two other interesting things on this chart. Right now, solar PV is up at 250 on the scale. It, of course, is a flat line. And if you ask, at this much cost of carbon, say $40 a ton CO2, what happens to gasoline? The answer is it corresponds to 35 cents a gallon increase in cost, or if you're in the UK, 5p per liter. Right? So the lesson here is that it is pretty inexpensive to get carbon out of power relative to getting carbon out of petrol. 35 cents a gallon means nothing on the scale of fluctuations we've seen over the last couple of years. And that's fortunate because most of the emissions are, in fact, from stationary sources. They're not from transport. Okay? So if anybody talks about a carbon market, the answer is it's got to be somewhere between $20 and $40 a ton of CO2 if you're serious about it. Anything less than that, and you're not going to have much impact. Anything more than that, and you're probably overdoing it. A word about buildings and energy efficiency. As I said, half of the world's energy is used in buildings. The technology exists now. It can, of course, be improved, but it exists now to significantly reduce that demand. The challenges are really in building codes, consumer behavior, and how anybody is going to make money by reducing energy and building demand. Cities, urban energy systems are another big lever that as we build new cities, particularly in Asia, if the cities are designed right, we can cut energy use. It's got to do with patterns of residence versus business. It's got to do with transport of people and goods. It's got to do with building design altogether. Probably lots of opportunities there. And in fact, we're sponsoring a research program at Imperial College in London to look at those issues. Okay, almost ready to close. Let me talk about where I think things are going to be over the next 30 years. Hydrocarbons are going to continue to dominate transport because of their high energy density. For those of you who are scientists or engineers, an amazing number you'll appreciate is that when you put the nozzle of the gas pump into your gas tank, you're wielding about 15 megawatts of power as you pump gasoline into the tank. That's a big number, right? More energy density than TNT in the gasoline. So we're going to see a succession of conventional crudes, heavy oils, biofuels coal and gas to liquids, they will ensure continuity of supply at a reasonable cost. We can double vehicle efficiency easily. Hybridization, plug-in hybrids, advanced gasoline engines and diesel, all of which can be used to improve vehicle efficiency. It is a question of having the political will and economic fortitude to do that. Local pollution is controllable at cost, as I said, and the CO2 emissions from transport are now 20% of the total. If we can cut that by a factor of 2, you're down to 10%, and then it hardly matters relative to the rest of the sources of greenhouse gases. Hydrogen in vehicles, much touted by the U.S. government, is a long way off if it's there at all. It's got lots of problems with it. I don't want to go into them, just to say there are many more options that are more viable, particularly in the short to midterm. For power, coal, for reasons of energy security, and gas for reasons of cleanliness are going to continue to dominate. Capture and storage of the CO2, hydrogen power, will be practiced if the CO2 concern is going to be addressed. We project that when the technology is developed, it'll be about a 30% increment on unsequestered use of coal. Nuclear, for reasons of energy security and CO2, will be a fixed and probably growing fraction of the mix, but not a particularly large one. In fact, I would assert that if the world does get serious about CO2, that these two technologies, capture and storage and nuclear, in some mix, are absolutely essential to dealing with the problem. If you haven't practiced one or both of them, you're probably not going to stop the rise in CO2 emissions. Renewables will find some application, but will remain a small fraction of the total. Wind will probably get to 10% of electrical power. Solar will do whatever it's going to do, probably not very large. However, I would say that advanced solar, advanced materials that are much more economic and friendly than the current silicon, is a wild card. If that's developed, you could see solar really take off and make a material difference. Demand reduction. I'm somewhat cynical about this. It will happen only where it's economically effective, namely if you raise the cost of energy so that people will look for efficiencies, or it's mandated by policy. And major increases in cost or stringent policies are something that governments find difficult to do and stay in power. So it's going to be tough. And CO2 emissions and concentrations are going to continue to rise unless the globe really gets its act together. Last word about the steps around the technologies. I want to say a word about policy. What we really need are technically informed, coherent, and stable government policies. And many people have said that that's an oxymoron. I think the way you get there is by educating people. You need to educate the decision makers so that they can understand what the right choices are, and you need to educate the public so that they can support the decision makers making what will often be difficult decisions. For technologies in the short to midterm, you've got to avoid picking winners and losers. The best way to do that is emissions trading, let the markets work, and have a level playing field for all applicable technologies. If the goal is to reduce CO2 emissions, for example, do not demand that it come only from renewables, but allow capture and storage or allow nuclear to compete on those same bases. For longer-term technologies, support for pre-competitive research, lots of possibilities there that the government should be supporting. From the business side, business needs a reasonable expectation of the price of carbon. If a large company like BP is going to make a significant development in carbon-free or low-carbon power sources, it needs the assurance that over the 20 or 30-year lifetime of that project, that the savings in carbon are going to matter economically. Right now, it's difficult when government turns over every 2 years in the U.S., the House of Representatives changes, and so on. It's difficult to see how one is going to get that assurance. And finally, the universities and the labs really need, and in fact are starting to come to grips with energy research. It's not only about the technology, but it's also about having people who understand the interaction between policies and technology as well. That's really important if the world is going to address some of these problems. And with that, I thank you for your attention. I'm happy to take some comments or questions.
Yeah, Stephen, has BP or any other country or university addressed the issue of the extraction of resources from the core of the Earth, from the crust of the Earth, rather? Excuse me. What kind of implications what happens with all this we've been removing?
You mean in a physical sense?
Yeah, the mechanics of the Earth.
Yeah. You know, the oil we're going after right now, for example, in the Gulf of Mexico, is 27,000 feet down under the surface. And pulling that oil out has essentially no physical effect at all on the surface on top of it. It's true if you look at very shallow things, you can see subsidence and so on and movements of the ground, but all of that oil is long gone. It's the deeper stuff that we're after now, and there's no physical issue. As people talk about hydrates, clathrates, which are phases involving water and methane, they tend to be shallow, they're physically unstable, and there is great concern about geotechnics, movement to the ground, if the world ever started to produce those resources, but they're not being produced, in part because we don't know how to solve that problem.
Yeah, thank you. More or less in the same line as the previous question. Have people considered perhaps addressing climate change through maybe, I don't know, spreading aerosols in the atmosphere, and also maybe adapting to climate change, the more economically viable option, preventing it?
Yeah. So, you know, there's a whole series of categories of steps that I think the world is going through. The first is obviously efficiency. The second is mitigation or the decarbonization of our energy sources. The third is adaptation, living with climate change. And the fourth is the example of which you gave is an example of what's called geoengineering. My own sense, and I'm now about to say something that's politically incorrect in some circles, is if you look at the picture I painted for you and the facts, it's pretty clear, to me at least, that the world is going to find it very difficult to stabilize at 550, and we're likely to go significantly higher in the course of that century, in the course of this century. If you, and there are good reasons to believe some of the model projections that severe and sudden changes in the climate can take place, we had better have ready, thought through, costed, and understand the implications of various interventions in the climate system, understand when they might be deployed in order to mitigate some of the possibly sudden changes that might occur. As somebody said in a discussion today, we've been talking about this quite a bit in small groups, it's like asteroid protection, you know? I mean, it's a perhaps unlikely or infrequent event, but you had better think through and have ready the methods to deal with it. Okay, good.
Steve, this is Ramanathan from Scripps. I think we have to be a little bit careful about the biofuel issue. There could be climate implications. For example, if you take semi-arid soil and plant corn or sugarcane, you will increase the absorption of sunlight so much, it could offset any benefit.
Yeah.
And likewise, if you replace gas with biodiesel, which puts out elemental carbon, which has a huge heating effect. And there also, as you know, the nitrous oxide issues. So I want to find out to what extent your institute in Berkeley or industries are working with climate scientists before they release new technologies.
Yeah. So the issue of, let me call it sustainability of biofuels and their collateral impacts is certainly something that's very much on our minds as we go into this. The issues of albedo change, for example, we've not explicitly considered. I mean, we've not done any work yet, but it's certainly something that will be on the agenda. I think on a lot of these issues, these are very good questions you raise. They're not something to shy away from, but they're in fact things to investigate scientifically and understand how we can deal with them. Just as a side remark, you mentioned corn and sugarcane. those are probably exactly the wrong things to be growing. We're going to look at energy crops in a serious way. Yeah.
Ron Waltz, General Atomics. If I understood what you said, the best thing the government can do is simply to set a carbon tax per ton policy or phase it in some way to know the number. Is that true?
So I think it needs to set a price for carbon or put in place a mechanism for determining a price. We actually think a tax is not the most efficient way to do it because it doesn't allow the system to adapt to find the most efficient ways of reducing CO2 emissions. We much prefer a cap and trade system whereby there are certificates that allow you to emit, and these are traded and there's a market for them and so on. In principle, at least, the system will then find the optimal means of reduction. The problem with that is perhaps twofold. It's got its downsides. One is that you're never sure exactly what the price is, particularly 10 or 20 years out. Of course, we have that kind of uncertainty all the time in the oil markets in BP's business, but we have a lot of experience with oil markets and can reasonably project what might happen. CO2 markets are too new to have that. The second, of course, is that in markets there's always the issue of leakage and people finding ways around the system. That's what you want them to do in some sense. They're supposed to game the system to find the most efficient reduction, but there are problems potentially with that as well. The other way you can do it, of course, you can set a tax, you can do markets, and the third is just by regulation, which is probably the least efficient of all.
You're Glenn Ramback, energy consultant. Your comment on the 3 E's and needing to budget and consider the economic costs of different options. A lot of different options come with carry along different externalities or impact different externalities differently. Is it at all reasonable to try and internalize those externalities, or do they tend to be too subjective to do so?
Some of them you can do. So CO2, the greenhouse gases, you can pretty well quantify that, and we can talk about a price per CO2. One that we wrestle with a lot, and I don't have a good answer for. If somebody does, I'd love to hear it, is the security externality. How do you put a price on energy security? I don't know how to do that. If you do, I'd love to talk about it later. Yeah, well, you're right.
Jose Boedo from the CR. You pointed out the obvious difficulties of trying to flatten out the CO2 concentration to 550, and due to the mismatch in timing cycles and all that. But what about reforestation, a massive reforestation program that essentially will trap the CO2 at low cost?
Yeah. So first of all, I'll say I'm not an expert on the carbon cycle, and I will defer if someone knows better than I what I'm about to say. Part of there is deforestation going on right now, and it's putting CO2 up. That's the piece I showed from changes in land use. You can easily restore that. The problem is because the CO2 lasts a long time in the atmosphere, you've got to take the carbon out for centuries, several centuries. The lifetime of forests is what it is. The trees decay and go back up and so on. So you can get some, temporary relief, but eventually we're pulling we're pulling carbon out of the ground, introducing it into the atmosphere, ocean, land system, and you've got to take the carbon and take it out of that system for a long time. I don't think forests do that very effectively. And then there are issues associated with the albedo of forests. As you may have read recently a paper in Science, temperate forests are not a particularly good idea from an albedo point of view. So it's complicated, as in all these things.
So Steve, Mike Campbell from General Atomics.
Hey, Mike. Yeah.
You talked about the public issues with nuclear, which I think everyone is well aware of, and has talked about a lot. But when you look at the amount of sequestration that must take place for the terawatts of power that coal would have to produce, do you get a sense that the public will accept that amount of CO2? I mean, Lake Nyos is, I guess, the poster child. For those who want to do a large sequestration program. Do you have a sense of that?
No, I think that's an evolving issue. I mean, for those of you who don't know, Lake Nyos is a lake in the Cameroons, I guess, that had CO2 building up on the bottom of it due to various biological processes, it overturned catastrophically, sent a cloud of CO2 down the mountain, and killed some number of people and even more cattle from asphyxiation, basically. You know, we're not going to see that kind of catastrophic leak out of, remember, these are big reservoirs under the ground with not very many wells associated with them. It is an open but very plausible issue that the CO2 will stay down in the depleted oil reservoirs. And we and other people are engaged in experiments to try to demonstrate that. However, those reservoirs have a limited capacity. If one is going to do this on scale, we're going to have to sequester in saline aquifers. There's a lot of capacity there, but there really needs to be a set of experiments and studies done, modeling, to demonstrate that you can keep the CO2 confined for of order 1,000 years in these saline aquifers. But we should be getting on that rapidly. Again, part of the problem here is that you're going to get locked in as you start building power plants. China's building one power plant a week, 60 gigawatts a year of electrical capacity. You get locked into the emissions from that plant for 40 or 50 years. And so we need to start very soon if we're going to have any noticeable impact on these things.
Bob Kahn, Steve.
Hey, Bob.
One of the things that you showed, which you didn't comment on, or you commented, but I want to ask you a different kind of question about it. We have in California decoupled GDP growth from energy use. Yeah. And even in the large-scale graph you showed, the country has done it, not as well as California. But by and large, in the 60s and 70s, the mantra was, if you want to have progress, you have to have, there's a coupling between GDP and energy use, right. And which do you want? Right. We've established over 25 years that you can decouple GDP growth and have progress in that sense, right, without enhanced energy use per capita. Go ahead. So the question, I guess, is, and you've seen by using different sources, particularly France and the other charts you've had, if you go to 80% nuclear, you actually get off that entire curve that's a worry. Yeah. So on those two questions, one, that you can, in fact, at some point and in some way, decouple GDP growth. You look now at China, at India, and at the others. What are the lessons that we've learned over the last 30 years that ought to be applied there to get that decoupling into place? And secondly, what's your view about nuclear? France is basically a demonstration project.
Yeah. On the decoupling first, I think it's pretty clear there is a decoupling, and you can see it not only in the U.S., but in the European countries as well. But they're already up at $15,000 per capita GDP. China's a long way from that. It's a factor of 3 away, right? So the 15 years till China gets here. I think this is about building buildings, roads, infrastructure, industrialization, and so on. Second, this is somewhat misleading, perhaps, because we've moved a lot of our heavy industry offshore, and we're not counting in the energy use here, the imputed energy use from the goods that we're purchasing at low prices from these countries that are down over here, right? So that's the second. What do I think about nuclear? Absolutely essential if the world is going to deal with CO2. If the world is not going to deal with CO2, it doesn't play much in security of supply. There's no a priori reason for the U.S. to be doing it, except for the low emissions. If it does want to address emissions, it's absolutely essential. And then it's got all the collateral or subsidiary issues, safety, waste, proliferation, on and on, which you know much better than I. So BP is not doing nuclear. I think we believe it's got to be a piece of the solution, but there are other companies that can do nuclear much better than BP can. Yes?
Gabriel Rubez, UCSD. You paint a picture which is that we will have constant oil, reasonable constant oil for the next 30 years, while even, let us say, reputable newspapers or scientific media paint a completely different pictures about, King Hubert's peak, Simmons oil, and so on and so forth. Right. And, we are all scientists. Can't we agree on something?
Yeah.
I mean, it's not like, oh, you are, both camps are diverging by 5 or 10 or 15%. Both camps are diverging.
Yeah, yeah. So, partly it's a question of language, and partly it's a question of outlook and perception. The peakists, of which Hubbard is probably the most famous, tend to come from a geological background. The geologists are trained to go out and find conventional crude oil. And admittedly, that's a finite resource, although I showed you what the IAE projections are, its availability. The people who are the anti-peakists tend to come from the economics school, and the argument they would make is that as the price of oil goes up, people will explore and produce oil from more difficult places. They will turn to heavier oils. Eventually, they'll start making transportation fuels from coal, et cetera, et cetera. And so the world will not run out. We may pay more for it, or it may come from less conventional sources. But it's hard to see it peaking. So in some sense, it depends what you mean by oil, right? Okay. I think that's the disconnect. Sufficient to say, though, the world has managed to meet demand with supply for the last 150 years. What you see currently is that spare capacity is going up. You see OPEC cutting its production in response to fall in demand in order to keep the price up. So it seems unlikely that we're going to run out.
Doug Jorgensen, graduate student, UCSD. On the chart that you had that showed different sources of carbon for the U.S. and for the world, and you had the potential for biofuels at the end.
Yeah, right. We can find that. Go ahead.
Does that consider, so that considers also I heard somebody else had concerns about maybe the albumin, I don't know what that is, the solar absorption of
albedo.
Plants.
The albedo. Yeah.
Is there any serious research that you know of that could decouple the biomass potential from land use, like aquatic agriculture, things like that?
Yeah. So, first of all, let me say about this estimate, which is from the so-called billion-ton study, assumes better use of stover and straw from the corn and wheat. It assumes better use of forests, and I think about 40% of that comes from energy crops, dedicated energy crops like switchgrass, miscanthus, and poplar. So in many ways, it's in addition to food. The second is not discussed here at all, but on people's minds is the possibility of using algae, for example, growing algae. Sure, why not? Okay, let's look at that. In the end, it's a question of, as we were discussing earlier today, systems engineering and cost. And there's a benchmark there. If you can get down to that cost and scale it, let's go for it.
My name's Ron Petzold. I don't know the answer to this question. I have heard that the energy in versus energy out may be low for biomass. Is that true or not?
So let me address the energy versus in versus out. I've actually got a chart. Let me just pull that one up. I can talk through it here. It's one I missed. Okay, so this is about corn ethanol. Just to go through the numbers briefly, 20% of the U.S. corn production last year versus 6% in 2000 went to make ethanol. It's growing rapidly. That's why the price of tortillas is going up. And that 20% displaced only 2.5% of the gasoline demand in the country. 17% of the corn production was exported last year. The energy and environmental benefits are limited when we make ethanol out of corn in this country. But here's the energy discussion. To make a megajoule of corn ethanol, according to a study by Alex Farrell and collaborators up at Berkeley, published in Science about last January, a little more than a year ago, it takes about 0.9 megajoules of other energy. So 0.4, and of that, 0.4 megajoules is coal, mostly to make the electricity to run the process. 0.3 megajoules is gas to make the electricity and to run the distillation columns. 0.04 megajoules was nuclear and hydro. 0.04, that was again to make the electricity. But the interesting number is 0.05 megajoules of crude. So you took 0.05 megajoules of a liquid fuel and made 1 megajoule of a liquid fuel. You multiplied the liquid energy, the imported crude, by a factor of 20. That's a good deal. Even if you use most of the energy in coal and gas in order to do that, because what we want is liquid fuel. And we don't care whether it's 0.9 or 1.1 or something. If I told you, here's a lump of coal, and I'm going to convert the thermal energy in that lump of coal into electricity and lose 60% of it in the process, you wouldn't care, because you want the electricity, you don't want the thermal energy. In the same way here, we don't want the coal and gas necessarily, we do want the liquid energy. So from a security of supply point of view, this is a good deal. From a greenhouse gas point of view, it's not great. It's only about 18% less than gasoline. The advanced biofuels should be able to do 90% if we get it right. So that's the story on energy in versus energy out. You've heard big debates about it probably. The bottom line is it doesn't matter.
Ralph Brunner, UCSD. And I have a question. I think you made a really good point with your education point. But I think we have to focus more on that. I know, for example, in Europe, a law is coming out pretty soon where you have to use energy-efficient light bulbs, for example, at home. Or government workers are running around and doing measurements on windows, how much energy you lose, especially in winter times. How long do you think it will take to actually educate people to get more conscious about these issues? That you actually change all your light bulbs to something like that, or you go from a one-side window to two or three-side window?
Double glazing. So the light bulbs are an easier thing to do, right? I mean, it's almost economic now to do it, and the consciousness is raising rapidly in the U.S. for that. Although some people still don't like the color of the compact fluorescence compared to the incandescents. The double glazing and so on is much harder. It's a bigger investment, longer payback times, and so on. I think you're going to have to do that by building codes, ultimately. You're either going to have to impose it by regulation or do it by price and make the gas so expensive. Nobody likes that. I mean, as was remarked, California is one of the most energy efficient states. It's also one of the most emission light states, but electricity is probably one of the most expensive in the U.S. here, right? About 15 cents a kilowatt hour. You can find parts of the Midwest where it's 5 or 6 cents a kilowatt hour. So, yes, efficiency, but it costs money to do it. Yeah.
You spoke about, sorry. Could you comment on the role of fine particulates as reflecting sunlight versus gases and what the quantitative effects between those are?
Yeah. Ram has unfortunately left, but he's the world's expert on that stuff. The greenhouse gases are, 2 watts per square meter net increase. The aerosols, both direct and indirect effects, are somewhere between 1.5 and 2 watts cooling net. So the black carbon that he talks about is 0.8 warming. And so they are comparable effects. If we clean up the aerosols a lot, the anthropogenic aerosols, we'll see the temperature go up palpably. Of course, we get the benefits from the health effects and the aesthetics and so on, but the aerosols are masking a fair bit of warming.
Could you comment on either BP's or the industry's interest in 2 fuels that weren't mentioned here? One is biobutanol as a direct gasoline replacement, and the other is dimethyl ether, which is used a lot in China for stationary power.
So, I mean, biofuels is a whole discussion which I'm really sorry I didn't get a chance to go into just for time. Ethanol is the most common gasoline substitute right now. It's the molecule that God gave us some thousands of years ago. It's got great uses beyond fuel. But in fact, it's a pretty lousy fuel. The energy density is only 2/3 that of gasoline. It picks up water. It's corrosive to gaskets and so on. It's not very good at all. The biology is beginning to let us make better fuel molecules. Biobutanol is the next most obvious one. For those of you who don't know, it's 4 carbons and an OH. Ethanol is 2 carbons and an OH. 90% the energy density, not hydroscopic, not corrosive, et cetera, et cetera. The challenge is that, and we in DuPont have been working on that for a few years now and are getting close to commercial viability, is to be able to get the bugs to ferment the sugars to biobutanol. Extensive modifications of the microbes in order to be able to do that. The DME that you talked about. So